Today I'm just going to introduce you to my research project on Epsilon Aurigae. I'm going to talk about why the star is so interesting, how we collected the data, and then how we analyzed the data and the results we got. So what is Epsilon Aurigae? Epsilon Aurigae is an eclipsing binary star system, a system of two objects in space, usually stars, which are so close that their gravitational pull creates a common center of mass for them to orbit around. So in 1821, Johann Fichte was credited with documenting the variability for the first time. And then for the next century, they were looking at the star and noticed that almost every 30 years, the star would become about 50% dimmer for 2 years and then return to its normal brightness. So in 1928, Harlow Shipley correctly predicted that there was two stars almost equal in mass in the system. So then in 1971, Robert Wilson found that there was a tilted disk in the secondary and had a central opening which explained the mid-eclipse rebrightening and showed that they were correct about that. The previous campaigns focused more on the spectra of the secondary during the mid-eclipse. This research, which began by former student Sybil Foster, is more on the changes in the primary out-of-eclipse. So the behavior of Epsilon Aurigae is that it is eclipsed every 27.1 years by its secondary companion. The last eclipse was from 2009 to 2011, and the primary has been determined to be an F-type supergiant. So you can see in the pictures that the pre-eclipse it's just the primary star, and then in November of 2009, the secondary disk starts to come into the frame and take away some of the brightness from the primary. So there's some unusual characteristics of this binary system. You can see that the primary is an F-type star. It has a temperature of about 7,750 Kelvin. The secondary star is now considered to be a B star, which is a lot hotter at about 15,000 Kelvin. The disk is only about 550 degrees Kelvin because it's a lot cooler. So what is an F-type supergiant? You can see from this HR diagram, which is just a diagnostic plot that astronomers use to determine where in their life the star is. You can see that the temperature increases to the left, and that up is the luminosity. Since it's an F-type star, we would start about right here and go straight up. Its luminosity is about 10 to the 4th, so it's going to be up in the supergiant category. There's a thing called an instability strip, which is this arrow I put in right through Polaris. Epsilon Aurigae is right on the corner of the instability strip, which gives it its variability. So with this photometry, which is just measuring the brightness of the star, I downloaded data from the ADSO database and did a Fourier transform on the data and found that there was a 75-day period in the fluctuation of the brightness, which was a little bit more than what Sybil found, but after 4 years of data, it's probably what it is. So analyzing the spectra, there's a few things that we have to do first. We have to measure the continuum line, which is basically the basis for the feature. And then we measure the equivalent width, which basically turns the feature into a rectangle and measures just the area of it. So then there's some characteristics to it. This feature is actually H-alpha, which is just the alpha hydrogen line. You can have emission or absorption. Emission is above the continuum. So on the left side, it's blue emission, but if it peaked above on the other side, it would be considered red emission. So just some instruments that we used and the data collected. We collected spectroscopy and photometry from May 2011 to about 2015. We actually collected some April 1st. We used the SE200A Eclipse spectrograph attached to the 20-inch telescope at the UIS Henry R. Barber Observatory. I used the program SpecView and VStar to analyze the spectroscopy and photometry. So this is H-alpha again, the changes in the spectra. So in October of 2011 is the blue, so you can see a high absorption. And then in March 2014, the absorption starts to shrink, and the emission is showing more than it did before. But you have to keep in mind that both of these are after the eclipse, so it's still changing while out of eclipse. So the measurements from the equivalent width I plotted against the dates that it was collected. And you can see that for the iron lines that it doesn't change very much, which is accepted for a star because it's coming from the actual primary star. So we're not expecting a lot of variation in that. We want it to be pretty much constant. But then what is interesting is that the potassium-1 lines are used to probe the protoplanetary disks, such as the secondary star. So since there's a decrease in September and then it starts to level off, it's a good probability that that is part of the disk right there. So instead of being the opaque disk that we can't see through anymore, it's transparent and we can see through it. It's collecting from the spectroscopy. Because from the photometry, we didn't see a fluctuation in the spectra. So then measuring the equivalent width of H alpha. H alpha is interesting because mostly stars are made of hydrogen. So it's important to measure it because it tells us the extent of the cloud and its age and things like that. And since H alpha lines saturate so easily because of the hydrogen, it's the main component of stars. So in summary, with Epsilon Aurigae, there has been a continued fluctuation in the brightness. I performed a Fourier transform which showed that there was a 75-day period in the brightness of the star. The potassium-1 line showed that there was still presence of the disk even after the eclipse ended months after. And we've also noticed that H alpha is still changing. One thing we aren't sure of is if it's the star itself or the material around it, since there's an increase in the emission and then there's less absorption. So, thank you.
Any questions for Shelby? Stay out there, Shelby. Any questions for Shelby? Up on top.
Shelby, how do you measure the brightness of the star?
The brightness is used with photometry, so we take the telescope and we use CCD filters, and we collect the light through a slit, and then we dart subtract it to get just the light from the star. And then that is reduced and uploaded to the AVSO database, and that's when I downloaded it and then graphed it.
So when you're collecting this data, is it over a long period of time? Because I'm assuming that between here and there, there's lots of things that go between us. You know, so
yeah, this data spans about 4 years. So the separation, the equivalent with, there's no data from the telescope between there. So the spots aren't because there's nothing, it's just we didn't have a good sky to collect it. Yeah.
Going back to the potassium-1 line, so the absorbance is decreasing, is that what you're saying? Or
the equivalent width is decreasing. So the absorption line was decreasing, and the emission is starting to increase slightly.
And that would be coming from the star?
No, this is from the disk. So this is from the secondary protoplanetary disk surrounding it. We think that the disk, it's pretty much opaque, you can't see through it, but there might be some that you can see through on the very edge, which is picking up the potassium, and you can't see it in the brightness because you can see through it, basically.
And on this graph, when did the eclipse end?
The eclipse ended in May 2011, so somewhere in here.
Oh.
So this is September, which is well after the eclipse ended.
Any other questions for Shelby? Well, let's thank her again.